Hey, can everyone hear me in the back? Yeah, that's awesome. So thank you for joining. I'm Yuval Avrahami, and this is Shaul Ben-Chai. And today we're going to try to answer a simple question. Does a single container escape allow an attacker to take over an entire Kubernetes cluster? And we hope that by answering it, we can share some insight that we learned into Kubernetes privilege escalation. So a bit about ourselves. We are cloud security researchers from Palo Alto Networks. So we do vulnerability research and threat hunting in the cloud. So searching for vulnerabilities in infrastructure components of the cloud and also in cloud service providers. And we also look for threat groups that target cloud environments specifically. So that's enough about ourselves. Our agenda for today, we're going to start off by talking about container escape, this threat that we keep hearing about, and try to really understand what's the actual blast radius. We'll then do a quick Kubernetes 101 just to get everyone on the same page. We'll continue to talk about what happens after a container escape, what resources does an attacker have to spread in the cluster, and we'll see several attack classes that attackers can abuse in order to escalate privileges. We'll then have enough resources in order to answer our question, does a container escape equal full cluster compromise? And we'll answer it both generally, but also specifically in the most popular Kubernetes platforms today. We'll wrap it up by talking about some of the fixes that the affected platforms put out. And we'll also talk about some takeaways that you can take from these presentations. So with that, I'll pass the mic to Shaul to talk about container escapes.
Thank you, Yuval. Hello, everyone. Let's start to talk about container escape. So ever since container came into our life, we've been hearing more and more about container escape in a sense of vulnerability, kernel vulnerability, misconfiguration, vulnerability in Docker and Kubernetes. And here in Black a few years ago, there was a great talk about container escape. So the obvious question is, do container actually contain? There is no doubt that containers are great for packaging and deploying software. This is the reason why we all use them. But they are weak security boundary, mostly because of the shared kernel. In a nutshell, the same Linux kernel vulnerability that allow unprivileged user to become a root can often use to escape from container and take over the underlying host. That's because the Linux kernel attack surface is simply too big, and we probably continue to see more and more variants of container escape. Only in 2022, we introduced at least a dozen vulnerability of container escape. But escaping from a container can also happen because of misconfiguration. The most known one is privileged container with access to the host. We also introduced threat actors that exploiting container escape to spread in the Victor environment for crypto mining, for example. So we understand that container escape will probably continue to happen, and it's here to stay. So we must understand what is the impact. The obvious impact, in Kubernetes at least, is a compromised node. An attacker will previously compromise one container or one pod, and now has a control over the entire node, probably for more business logic or more compute resources for crypto mining, for example. But just imagine that an attacker is an ambitious one, and he might be not satisfied with only a single compromised node. He maybe might want to take over the entire cluster. And this is the question we will try to answer today. If a scenario of a single container escape could be escalated to full cluster admin access. And if you are asking yourself what is the motivation, he may want to take over other services or databases or even get some credential secret to try to spread out outside our cluster to other interesting environments. Just a quick terminology. We're going to use today two terms, admin and admin equivalent. When we say admin, we're meaning that you can do any kind of operation, all the namespaces. And admin equivalent is mean that you have enough permission that in one or two trivial steps, you can become an admin. But just before we continue, we will do some quick Kubernetes 101 just to make sure that we are all on the same page. So in a one sentence, Kubernetes orchestrated pod, containers on a node on virtual machine. And basically today, it's everywhere. Mostly heavily used in Linux workload, mostly on cloud, on-prem, and it's a very interesting environment for an attacker. We have the API server, which is the cluster gateway or brain, and user can communicate with the API server using Kubernetes, using kubectl, the Kubernetes CLI tool. Then the API will schedule a pod on the underlying node, and will operate this kind of operation. A little bit about authentication. You can either authenticate using certificate. This is how user and nodes are authenticate, or you can use service account token. This is how pods are authenticate. And a little bit about authorization. Permission expressed in Kubernetes as a verbs and resources, like list secret, create a pod, update node, delete services, and so on. And those permissions group into a role. And when you want to grant permission to some identity, you use role binding to do this. And if it was a little bit complicated, let's do a quick example. Here we have our role, who can list services and list pod. And we want to grant this permission to our identity, to our pod. So we will bind this role to the service account. And when the pod will running, he will use this token. In our case, we can list services and list pods. So that's enough for the Kubernetes one-on-one. Back to our research. Let's try to understand now what will happen once an attacker can escape from container. So before, in order to do so, we need to understand which kind of credentials we have in our node. So the first is the kubelet permission. The kubelet is the node agent who can manage and facilitate all the node. So obviously has a set of permissions that allow him to do this. But fortunately, Kubernetes restricted the kubelet permission. And if we are talking about meaningful attack, so the kubelet is not the address. It's true, an attacker can manage to perform some limited attack like denial of service, or maybe to get some primitive read or something like this. But if we are talking about meaningful attack like full cluster admin, so the kubelet is not the address. But there are also another set of credentials on the node, which is the service account of the neighbor pods. And the permissions are vary because it depends on which application running on your pods. It depends on your nodes. It depending on which platform you are running your cluster. So an attacker might be, and might be not, has a way to succeed a powerful permission, but at least he has a chance. Because the kubelet permission will be the same restricted permission on every single node. And today we're going to talk about this scenario exactly, where we have an extremely powerful pod, and we name it trampoline pod. Pod that can have enough permission that can bounce you around the cluster, to jump to other node, to get some high privilege, and basically let the attacker have some fun in your cluster. So where those trampoline pods can be? Let's see which kind of pod are running in our typical average node. First, the application, like Redis, Nginx, MongoDB, or our Python or Golang application. Then commonly at Kubernetes, we have the add-ons, like Itio for service mesh, or Prometheus for login, or Opa Gatekeeper, or Kinvero for policy enforcement. And finally, there is the system pod, the infrastructure pod, like kubeproxy and core DNS. And those pods was already there when we are setting up our cluster. And it basically depends on which platform you are running your cluster. So as you already noticed, the system pods, and in some scenario also the add-on pods, are quite a blind spot because we didn't manage them configuration. Add-on pods we just install add-ons pods using a package manager like Helm, for example, and the author of the add-ons configured them permission. And for system pods, there was already there when the cluster was created. So, of course, we didn't control or manage them permission. And another interesting thing about system pods, and in some scenario also the add-ons pods, that they deploy and install as a daemon set, which means they are running on every single node in our cluster. So if a trampoline pod not installed as a daemon set is running only on one node in our cluster. So if an attacker has escaped from a certain node, he maybe and maybe not will be on the node that hosts these trampoline pods. And it's 50-50%, and maybe less because it depends on the number of pods that's running on your cluster. But if a trampoline pod is deployed and installed as a daemon set, an attacker guarantee to hit a jackpot because every single node in our cluster will run these trampoline pods. So the answer for our main question today, if a single container escape could be escalated to full cluster admins, the answer found in those trampoline pods that running on every single node in our cluster. So I'll switch it back to Yuval.
Thanks. Is my mic back? Oh, awesome. So as Shaul said, after a container escape, our golden ticket to escalate privileges relies on trampoline daemon sets. So we went out and tried to find where those trampoline might be. So this is how it looks like. We looked into the most popular Kubernetes platforms and looked into their infrastructure pods. And this is an actual example. We saw a pod that can list secrets, delete pods, create config maps, and update the status of nodes. And we looked at those permissions and we tried to ask ourselves, is this pod powerful? Are we looking at the trampoline? And we quickly realized that we don't know. We don't have the resources. We looked into the Kubernetes documentation. We tried Googling it. We looked into previous security talks about Kubernetes. And we quickly realized that there is actually no public list of powerful permissions in Kubernetes. Now, that is actually quite scary because without knowing which permissions are powerful, you can't really answer basic questions about privilege escalation, right? If I'm a defender, I can't really know if my publicly exposed pod can actually escalate privileges if I don't know if its permissions are powerful. And as an attacker, once I get a set of compromised credentials, I can't tell if they're valuable or not if I don't know which permissions are powerful, right? So we started working and trying to figure out which permissions are actually powerful in Kubernetes, and we quickly realized that a lot of permissions that we thought are quite benign were actually quite interesting if you use them in a creative way. So our approach to go about this is that we first defined what are interesting attack classes in Kubernetes, in our view, that can allow you to get meaningful privilege escalation. And then we looked over all of the permissions in Kubernetes and classified them based on the attack classes that they can enable. And this is the mapping that we came up with. We came up with 4 attack classes, about 20-something permissions mapped into each one. Now, we won't go into every permission and how it enables the attack. We have an actual a report that is published alongside this talk where you can see how each permission enables the attack. But those are the permissions that we identified, and we look at an example for each attack class in order to make them more real. So let's start off with permissions that allow you to manipulate authentication or authorization. Those are extremely powerful permissions that actually allows you to either impersonate other user or to change your permission, so freely manipulate the authorization of the cluster. One example for that would be the permission to escalate roles. That permission allows you to add new permissions to existing roles. So if I'm an attacker and I have a token which can escalate roles, I can simply go to the role of my service account and edit all the permissions in the cluster, which are denoted by this wildcard notation. And then immediately after I'm doing that, my token gets all of the permissions, which is beautifully illustrated by the token getting larger. The next attack class that we're going to talk about is permissions that allow you to acquire service account tokens. So either retrieve existing or issue new service account tokens. Now, what's the impact here? Well, it depends which service account you can issue tokens for, right? If you can issue tokens for powerful service account, then you got yourself a meaningful privilege escalation. If you can only, let's say, retrieve tokens of weak service account, that's not very interesting. Now, a very notorious permission in Kubernetes that allows you to, in this case, retrieve existing service account is the permission to list secrets. Service account in Kubernetes, up until now, were stored as service account tokens, was stored as secrets in the API server. So if you can actually list secrets, you can simply retrieve service account tokens and then use them to authenticate to the API server. And as I've said, if you get yourself a token for a powerful service account, you just escalated privileges. The next attack class, you're probably familiar with it from other systems, is RC permissions that allow you to execute code either on pods or on nodes. In this case, you're not necessarily escalating your privileges, right? It really depends on the permissions of the pod that you are taking over. But you probably get yourself more compute resources, right? Maybe more business logic, and as I've said, possibly escalating your privileges. Let's look at an interesting example for such a permission. It has a pretty confusing name. It creates the proxy sub-resource of nodes. Doesn't really tell us much, but it basically means that we can control kubelets. We can simply tell them what to do and tell them, hey, please execute code on your pod. One interesting thing about this permission that is you actually don't go through the API server, which normally has all of the login and auditing mechanism in the cluster, so you may be able to bypass some detections. Now, the final attack class that we're going to talk about today, and it's my personal favorite, permissions that allow you to steal pods. Basically move existing pods from one node in the cluster to another. And why would that be interesting? If we assume that we already compromised the node in the cluster, we might want to bring other pods to our node. Maybe because they host interesting business logic that we want to take control over. But in the case of this talk, it's probably because those pods have powerful service account. And if we bring them over to our node, they are going to come with their powerful service account token, which we can then abuse to escalate privileges. So we started with this by, let's see an example, yeah. This is a slightly more complex example. It takes two permissions to carry out the attack. The first permission is the update node status permission, and the second permission is the delete pods permission. Now, this is actually a great example of how permissions that might look not very powerful can actually be abused. When you first look at those permissions, you might think that you'll be able to get some maybe denial of service by deleting pods, but they can actually be used to steal pods. And let's see how. In this case, we assume that we already escaped a container and compromised a node, and we have a very powerful pod, an operator, on another node in the cluster, which we want to bring over. What we'll do is we'll first use the permission to update the status of nodes to set the pod capacity of all the other nodes in the cluster to 0, which we're basically making them unschedulable. The next step is going to be to delete the operator pod. And now when Kubernetes has to recreate that operator pod, it will conveniently have to create it on our node because it's the only schedulable node in the cluster. And we successfully brought the operator pod over with its powerful service account token. So that's how you steal pods. And if you remember, we started talking about Kubernetes attack classes to define what trampoline, what powerful pods are. So trampolines are powerful pods with permission to either manipulate authentication or authorization, acquire powerful service account tokens, execute code on pods or on nodes, and steal other pods in the cluster. Because those sets of permission actually get you a real shot of getting cluster admin. So Shaul and myself talk about a few subjects. Let's try to do a quick recap. We started off by talking about container escapes and understanding they are likely going to continue to happen. We then talked about how their impact largely is dictated by the presence of powerful pods of trampoline on the compromised node, right? And we define what are powerful pods. We also talked about how trampoline daemon sets install those trampolines onto every single node in your cluster. So if you want to really answer whether a single container escape actually equals cluster admin, What we are really asking is, are there trampoline daemon sets in the cluster? Who installed them? Are they common? And so on. And that's really what we tried to do in this research. We looked into the most popular Kubernetes platforms. Some of you are probably users of those platforms. And we looked for trampoline daemon sets. The platforms we looked into are mostly the infrastructure layer. So managed Kubernetes services like AKS, GKE, EKS, OpenShift. And we also looked into container network interfaces, basically the network infrastructure of the cluster. We looked into popular projects like Calico, Antrea, Cilium, and WeaveNet. And what we found when we looked at those projects back in February of this year is that most of them actually installed trampoline daemon sets by default. Another 12% installed them given a popular feature was enabled. This is actually a breakdown of the trampoline daemon sets back in February in each of those platforms. And so you can see which platform had powerful daemon sets, which were those daemon sets, and what were their powerful permissions. Again, we have a report with all of the details, so you don't need to take pictures right now, unless you really want to. So we looked at those daemon sets and tried to understand how powerful are they. Could they really allow you to get a full cluster admin by default? And in half the platforms, that was actually the case. In half the platforms that we looked into, the answer to our main question was yes, a single container escape allows you to take over the entire cluster. In another 25%, there were some prerequisites. For example, some feature being enabled. So we got mostly definitive answers for those platforms. Now, I do want to say if any one of you is running those platforms, you don't need to panic or something like that. This isn't an unauthenticated RC, right? There is a large prerequisites of a container escape happening. But it's also something to note to get your cluster security to the next level. So let's see how an actual attack on one of those popular platforms looks like. So we couldn't obviously demo all of the attacks. The one we're going to see is on Cilium, which is a very popular container network interface. It is what's powering the new data plane in a Google Kubernetes engine. The reason why we chose Cilium is that because it showcases a number of attack classes, and also Cilium maintainers did a great job of fixing every one of the things that we're going to show here today. So what is the scenario in Cilium? Cilium installs two interesting components to the cluster. One is the Cilium daemon set, a trampoline daemon sets that can actually delete pods and update the status of nodes. And those permissions, if you remember, allow you to steal pods. The second thing that Cilium installed is the Cilium operator pod, which can actually list secrets, which, as we mentioned earlier, allows you to acquire tokens. Now, our attack scenario here is that we managed to compromise a pod and break out. So we have a node under our control. And our goal is to get cluster admin, so get control over all of the nodes in the cluster. Now, we are going to assume that we are on the weakest node, so the one not hosting the Cilium operator, because that's simply the more likely case, right? If you have 10 nodes in your cluster and only one runs the Cilium operator, most of the nodes aren't going to have the Cilium operator. Our approach to get cluster admin is to first use the Cilium daemon set permissions to steal the Cilium operator, and then use the Cilium operator permissions to get cluster admin. So let's see how the attack plays out. We're first going to use the Cilium daemon set permissions in order to make other nodes in the cluster unschedulable, using the same technique that we described earlier, setting their pod capacity to 0. We are again going to delete the Cilium operator pod, forcing Kubernetes to recreate it on our nodes. Now we have the Cilium operator service account in our disposal, and we can use it to list secrets and retrieve service account tokens in the cluster. Now, the service account that we are going to target is called CRAC, which is short for Cluster Role Aggregation Controller. The reason why we are targeting this service account is because it can manipulate authorization. It can escalate roles and other permissions that we discussed earlier. The final step in the attack is going to use CRAC service account token in order to simply add all the permissions in the cluster to the role that is binded to CRAC service account token. So it's only 3 steps, but when you translate them to kubectl commands, it gets much more. So we're going to go over this demo now. It's going to run quite quickly. If you can't follow every command, that's not completely fine. We're going to have a walkthrough afterwards. And you cannot see the demo. So can anyone help me with that? Maybe something like this. Let's try. How about now? Yes, okay. So as I've said, the scenario is that we are in a cluster that installed Cilium, and we are trying to get cluster admin. Now, we are going to start by emulating a container escape, taking over a node, because that's the starting position in our attack. And we're also going to define a script, which basically what it does is harvest service account tokens from the node file system and configures our CLI that talks to the API server to use them. What we're going to do is check out where the operator pod is, and we can see that it's on another node in the cluster. So our first step is going to try to steal the Cilium operator onto our node. We are going to define a bash function, which is called patch node. What it does is simply patches the allocated pod of the node to be 0 using a JSON patch. So you can see that the operation that we are defining is replacing the status/allocatable/pod value to be 0. And then we are going to use that bash function that is powered by the permissions of the Cilium daemon set in order to repeatedly set the pod capacity of other nodes in the cluster to 0. Now we are doing it in a loop because the API server actually corrects that value. Now when we delete the Cilium operator, if all goes well, it must be recreated on our node, and we can see that it does. The node name is highlighted in red, and you can see by the bash terminal line that our node, the host name is actually this name. So now the Cilium operator is on our node, and we can continue to the second stage of the attack, which is to use the Cilium operator service account in order to get Crux token, right? We are first configuring our CLI to use the Cilium operator's token, and then we can see that we can actually list secrets in the cluster. So we are going to target the service account token of the cluster role aggregation controller, or CRAC in short. Here I'm going to make a typo, so that doesn't work. But now it does, and we got Crux token. We can configure our CLI to use Crux token. So now we are finally authenticated as CRAC. We got its token, and you can see that when we ask the API server, hey, can I escalate roles? The answer is yes. We are still not cluster admin though, as you can now see. The final step in the attack is to edit the role that is binded to Crux token to have all the permissions in the cluster. And that's what we're going to do now. We are editing the cluster role, and you can see that the cluster role will now have the permission to modify and escalate cluster role. We're going to just delete everything and only put wildcards there. Now, the second we do that, our token immediately should get admin privileges, and when we check our permission, it should say that we are admin. And we did it. We got admin and took over the entire cluster. And we're back. So what attack classes did we see in this demo? We started off by stealing a pod, right? Stealing the Cilium operator pod. We then used this permission to acquire a powerful service account token. And finally, using that service account, we were able to manipulate permissions in the cluster. So I think it's cool to see how the attack classes that we talked about earlier actually map to an actual attack. It's important to understand that we showed Cilium, but other platforms had very similar issues. Some are less complex, some more complex. We just needed to demo one of those. So let's talk about what platforms did when we talked to them about those issues. We actually reached out to every platform that we found trampolines in, and it was really actually a great disclosure experience. Most of them were eager to fix the issues, and you can see that most of them actually did. Google actually awarded us a bounty for this finding, which was quite nice. So most platforms were really great about this, trying to and were able to deprivilege their trampoline daemon sets, so they are no longer trampolines. So from 50% back in February, now only 12.5% a single escape equals cluster admin. while this is really great, you should also not get the wrong idea about trampoline not being relevant or something like that, because we only looked at the infrastructure layer, and most clusters also have a bunch of add-ons installed, also application pods. Those can also install trampolines into a cluster. Moreover, we didn't look into every Kubernetes distribution. We looked into 8 platforms in total. And the funny thing I want to say, and this graph doesn't represent platform-specific attacks, right? If a certain platform has a specific attack to it, which is not Kubernetes native, we didn't look into that. But overall, the platforms were really responsible about fixing those issues. Now, if you run Kubernetes, you might be wondering how you can identify trampolines in your cluster and what you should do about them. So I'll pass the mic back to Shaul to talk about identifying those.
Thank you, Yuval. Amazing demo and great findings. So when we start our research, we quickly understand that we need automatically way to identify those risky permission and those trampoline pods. So we wrote a tool that can use both for an attacker and both for defenders to identify and find those risky permission. The tool called Embark Police. It's a CLI, an open source tool that retrieve the Embark permission of pod, service account, and nodes in the cluster and evaluate them through policies written in Rego. We have now about 20 policies out of the box, each targeting different kind of privilege escalation technique, and it's customizable. You can search for any patterns in Kubernetes Embark and write a new policy, perhaps for platform-specific or a privilege escalation attack that we didn't cover. I really recommend that all of you to take a couple of seconds and run and flash the trampolines and the powerful permission in your cluster. And this is the output, how the output looks like. At the top, you have the policy and the severity. In this example, policy that search for identity that could launch privilege escalation attack by modifying pods. At the bottom, you can see the violated identity that have the problematic permission that enables the attack and the pod that actually has this service account. So you can run Embark Police also today to quickly identify those trampoline pods and the risky permission in your cluster. So I pass it back to Yuval for the takeaways.
Oh, thanks. So some takeaways that we think you should be able to, we hope that you can take from our research. So as we saw today, trampoline pods, powerful pods introduce new privilege escalation avenues into Kubernetes cluster, up to a point where a single container escape allows you to take over an entire cluster. And we actually saw that in a lot of platforms, that's actually the common case, right? Those attacks were powered by powerful permissions, and we hope that the framework that we introduced of classifying powerful permissions into the different interesting attack classes can help both defenders and attackers, pen testers, understand which are powerful permissions and which are risky pods. Now, it's important to understand that those powerful permissions, while we looked at them from the lenses of a container escape, they are relevant whenever you have a compromised set of Kubernetes credentials in order to understand whether those credentials are actually powerful. Now, we think that the root cause for the issues that we talked about today is that it's simply tricky to configure Embark permissions in Kubernetes. One side of it is that a lot of permissions that look benign are actually powerful, and we hope that the list of powerful permissions that we released here today helps cover that part. Another thing about Embark is that it isn't included in all of the compliance and security checkmarks and benchmarks and checklists for Kubernetes, meaning that it isn't one of those things that you check for or have to check for in order to get some compliance standards. So in a lot of clusters, Embark isn't really looked into too much. What that causes it brings a bit of false confidence, we believe, because you might have a cluster that passes all of the security checklist, all of the compliance benchmark, everything shows green, but you still don't realize that you're a single container escape from getting your whole cluster compromised. So our recommendation for defenders who want to tackle this issue is, first of all, monitoring your RBAC. You should be able to tell which are the powerful permissions in your cluster. And then you should be able to say, whether those are actually needed. And in the good scenario, you can actually maybe drop some permissions. We hope that you can use RBAC police to do that. Now, once you know which are the powerful permissions in your cluster, we recommend separating powerful pods from untrusted or publicly exposed pods. Not all powerful permissions can be dropped. Some of them are necessary. So you should be able to use this technique in order to limit the impact of container escape. Untrusted pod and a powerful pod running together on the same node is a pretty toxic combination. Now, one thing that we didn't get to talk about in this session is audit and admission policies. We have those in our report. Those can actually be used to detect and prevent some attacks. So for those of you interested, this is a link to our report. This is a link to RBAC police, and we'll be happy to take any questions that you may have. Thank you.